Hey, so let's discuss a little bit about solutions. This should be a lot of stuff that you're familiar with. Maybe not in the terms that I'm going to use, but certainly the concepts. So, a solution is homogeneous. Remember that word from the first unit. Things where you can't tell the difference of mixture. You can't see where the water starts and the sugar stops, or something like that. So, homogeneous mixture. There's two parts. There's the solute. The solute is usually what the solid that you're dissolving, because could be a gas or a liquid as well, but mostly we're going to think of it as a solid. And then the solvent is usually a liquid. In this case, we'll mostly be using water, but alcohols could be used as a solvent as well, something that dissolves something. So the solvent is the liquid, and the solute is what you're dissolving in the liquid, typically a solid. All right, so the rule of thumb. So solubility is defined as the grams of solute that are dissolved by the solvent. This is possible that nothing dissolves. Think about water and oil, right? No oil dissolves in the water, so that solubility is zero. The golden rule, speaking of oil and water, is that likes dissolves likes. So something polar will dissolve something else that has a polar aspect to it, and something nonpolar will need something nonpolar to dissolve in it. So polar solutes are like ionic salts, which all dissolve in water. We talked about this when we did that little lab in class. Hydrogen bonding materials dissolve well in water. Anything where you have something water can grab onto, you need that polar bond, that plus minus situation. Nonpolar solutes have a lot of CH bonds, diatomics like Br2 or I2, right? They Brinkelhoff, they don't have anything for water to grab onto. So you may be in a lab at some point where you see a situation like this, which will show you certain things that are soluble, miscible. Okay, miscible means mixable. It means that it would form a homogeneous solution. There wouldn't be a line. So if you take methanol and mix it with acetone, there wouldn't be a interface like there would with oil and water. But if you did hexane with acetonitrile, there would be that interface. Okay, so these pink things means there's going to be an interface where there's two layers, water and xylene, or water and a lot of things. I meant, yeah, see, water and a lot of things on this list. So that's just what that means. Okay, so think about again when we discuss dissolving, you're going to have a situation where the pluses and minuses need to be attracted to something, and water has, because of its polar structure, pluses and minuses that are going to pull us apart. I know I've shown this to you before. It's coming back again. So the reason salt dissolves in water, the reason anything dissolves in water, is because water has those charged areas, and they're able to pull it apart when with their charge. So here we have the positive hydrogens pulling away the negative chlorines, and the negative oxygens of water pulling away the positive sodiums. And that's what you need for something to dissolve in water. You need water to be able to surround something and pull it apart. All right. So if you have something nonpolar, okay, something with a lot of CHs in it, then that will dissolve nonpolar things because they can sort of interact in their nonpolarness, basically. Think about how water, if you put a bunch of magnets into a bag with a bunch of like dry pasta or rice or something, the magnets would have nothing to hold on to with the rice. So the magnets would stick together and sort of the rice would be together. And that's sort of like the oil and water. Water would have these magnetic attractions to each other, the plus minuses, and the rice wouldn't have anything to contribute to that. So if you threw in something metal like a paperclip, the paperclip wouldn't go in with the rice. It would go in with the water area, right? Because it's polar. It has that magnetic attraction to the magnets, whereas rice wouldn't have anything to offer that paperclip, so that it wouldn't go in there. So that's what's going on when you dissolve or don't dissolve things in water. There's this thing called a fatberg, and here's a picture of a sewer system. Fats, the reason you're not supposed to put them down your drain is because a fat has lots of CH bonds. It will not dissolve in water. You can see there's a whole pool of water here. This fat is not dissolving, and because of that, it doesn't go anywhere, and it can start clogging up the sewer system just like it does with your arteries as well. And the water won't do anything to this because waters and fats don't don't mix. And so fatberg is what they call those things. So at the end of the day, everyone makes a decision whether they're going to go into a woman's room or a men's room, right? And the same thing is true with anything that you would have to dissolve. You have to decide, are you going to go in the water or are you going to go in the nonpolar stuff? And if you move on with science, there's a lot of things we do here where we take advantage of those properties, that the nonpolar things will go into the nonpolar stuff and the polar things will go into water. So at the end of the day, everything has to make a decision which side it's going to go in. In fact, if you've ever gotten gum in your hair or anyone else's hair, peanut butter works, but water doesn't, because gum is not polar. There's nothing there for water to hold on to, but it is non-polar. So if you use coconut oil or peanut butter, which is very oily, that oil will help get the gum out of the hair. In fact, we could have that like that. The way soap works is soap has a little bit of both. Soap has a big, long CH thing that will attract anything that's non-polar, and it also has a charged area here, which is going to stick to the water. All right, so you have your ionic situation here, you have your carbonyl, big difference in electronegativity between carbon and oxygen. So this is a positive negative, and you have your negative positive. So the water would love this, would hate this. Fatty things would love this, hate this, and then so that's how soap works. And it sort of doesn't choose one. You know this, right? If you put soap in water, it gets all soapy, and that's how you know it's not choosing one side or the other. All right. So the other thing you need to know besides solute and solvent is saturated and unsaturated. And I'm making you do this thing. I don't know how I'm going to make you do it yet, but I'm going to make you do it. We don't need to listen to him. Where you shake stuff in and you see this concentration goes up. The concentration is measured in moles over liters. And the more you shake in, the more concentrated it gets. This isn't surprising, right? The more sugar you put in your iced tea. And then it reaches a point where, if you can look here, everything's just going right to the bottom of the water. It's not salt. Look how much I'm shaking it and nothing else is happening. That's concentration staying the same. So that's saturated. We say that's saturated because no more solid will go into that water. And if we added more water at some point, it might start dissolving it. But anyway, all right. So you should play around with this. The saturation point, so here's 1.3 molar. If we use something else like potassium permanganate, you'll notice it's not going to get up to 1.3 molar. It's much lower, 0.4. So different substances have different rates at which they're going to saturate, at which point they're not going to get into the water anymore. So you should play around with that, certainly, to get a sense of all that. There's also a little lab you can do from home. But saturated means the water has as much the solid as it can hold, and unsaturated means it can still hold more. And so graphically, we represent this with a line. There's sort of a line that separates the unsaturated from the saturated, okay? Anything below that line would be unsaturated, so more of your stuff, more of your solid can get into the liquid, and above that line, you're not going to get any more solid into the liquid. And here's some samples. Here's some ionic solids. You see, as the temperature goes up, they tend to get more soluble in water. The opposite is true with gases. They tend to get less soluble in water, and that should make sense. If you leave a soda in your car, all the carbon dioxide leaves your soda because it's heating up, right? Gases want to be free, so as soon as they reach the surface of the liquid, they just go off on their own. And so heating things up, and this is why global warming is such a concern. We can't have oxygen leaving our water systems, and because then there would be no life in water. All right. Dissolved oxygen. Obviously, water is always going to have that oxygen in it. All right, so ways you can increase solubility of solids. Again, if you've ever had to make iced tea or lemonade, you stir it, right? You agitate it. You crush the big pieces into smaller pieces so there's greater surface area, and you could increase the temperature to get things moving a little more so that it can pull things apart. Obviously, that's not true with gases, but it's very rare that you're trying to dissolve a gas in water. This is for solids. All right, so last and not least, the math you have to do. And I think this math is going to be pretty easy compared to what you've been doing recently. So as you saw in that little interactive here, right, there's this thing called molarity. And for different things, you have different molarities, right? The concentration, the more you shake in there, the darker the color gets. The darker the color gets, the higher the concentration. So you need to be able to solve for this. So let's take a look at that. Oops. So molarity, that concentration is called moles. It's how many moles of solid you have divided by liters of liquid. And so high molarity would be concentrated, dilute would have a low molarity, be a lot of liquid. That should come clear to you. So if I ask you to find the molarity of something that's 25 grams of NaCl dissolved in 2.5 liters of water, I need to take the moles of the solid, right, which is this 25 grams of NaCl, and divide it by the liters of solution of the liquid, which in this case is 2.5. So we know it's going to be divided by 2.5 liters. So what we need now is the moles, and we were given grams. And by now, I really hope you understand that 25 grams to be turned into moles, you need the periodic table, right? And we're going to go get sodium from the periodic table, which has a mass of 23, and chlorine, which has a mass of 35.5. And we're going to add those up. And we're going to get 58.5 grams. So that's 58.5 grams in 1 mole. And so we divide 25 by 58.5. And we get 0.427. So that's 0.427 moles. And so that's going to go in our numerator. And our denominator is how many liters of solution, which we're here in blue. And when we divide those, 0.427 divided by 2.5, it's 0.171. Wait, what? Yeah, 0.171. And that's a capital M for molar. That means moles per liter. And again, think about what moles per liter is. Moles per liter is, right, how much stuff you put in there per liquid, right? So this would be, if I lower this down to here, so our liters would be 0.5 liters, and then the molarity would be how many moles of drink mix or whatever it is you're using here there are in there. All right, let's look at equation or second example. All right, so this is whenever you have a solid like hot cocoa and you're dissolving it in water. So here's 20 grams of hot cocoa that I'm about to dissolve in water, and that is what you do with these problems. So now I'm giving you, here's our liquid, right? 3 liters. So at the bottom we have 3 liters. I'm not asking you for the molarity because I've actually given you that molarity. So that's going to equal 1.25 moles over liters. And what I'm looking for is the moles. So I'm looking for the moles here. And then I'm going to convert that to grams. So if X is here and you have 3 there, hopefully it makes sense that you're going to multiply the 3 times the 1.25. So the X moles is equal to the 3 liters times the 1.25 moles per liter. And then liters cancel, and that's going to give you moles. So 3 times 1.25 is 3.75. So that equals 3.75 moles. Now, what it asked for was grams, though. So again, we got to go to the periodic table, take 3.75 moles, and from the periodic table, we got to turn moles into grams. And potassium, right? So potassium's 39, and nitrogen is 14, and oxygen is 16, and there's 3 of them, so that's 48. So 48 plus 39 plus 14 equals 101. So this is 101 grams in 1 mole. And if you multiply that by 3.75, you get 379 or 378, so 379 grams. So you have to put 379 grams into 3 liters of water to make a 1.25 molar solution. All right, so the other situation, so this is whenever you have a solid and you got to weigh it out in grams. Sometimes you have a very concentrated solution like drink mix, which is already pre-concentrated, right? These little flavor enhancers. And you have to dilute it further so that it doesn't do more than you want it to. So for that, you're going to use this equation, M1V1 equals M2V2. And M1V1 is the molarity of the concentrated times the volume of the concentrated will equal the molarity of the dilute times the volume of the dilute. So when you do all this, moles will equal moles, and I explained this pretty well in a lab video that you should look at. All right, units must cancel. In order to cancel, they have to be the same. You are never wrong to put everything in liters for anything we do. Sometimes these will be given in milliliters. You should convert to liters. If you don't for these problems, it's not the end of the world because both sides will be milliliters, so they'll cancel. But as a good rule of thumb, as we learned with gases, just convert everything to liters. All right, so here's an example of that. We have a concentrated solution, 12 molar HCl, and we need a dilute solution. Our dilute solution is 1.25 liters of 3.25 molar. So our equation here is our concentrated times our concentrated is going to equal our dilute times our dilute. And so we have 1.25 liters as our volume. We have 3.25 molar as our concentration. We know on the concentrated side, we have 12 molar, and we're looking for that V1. So 3.25 times 1.25 is 4. Oops, that's not true. 3.25 times 1.25 says here is 4.06. So, all right, so 4.06. This 4.06 is going to equal 12 times V1. So in order to get this done, we got to divide both sides by 12, and we get V1 equals by 12. We need 0.338 liters. So we need 0.338 liters of that concentrated acid to make 1.25 liters of 3.25 molar solution. So what we're going to do then is take just a little bit of that concentrated acid and then fill it up with a bunch of water to the 3.25, 1.25 rather, 1.25 liter mark. So, and then that whole diluted solution will have the 3.25 molar concentration. Okay, so here's another example of that. Your original solution is 125 mils of 2.75 molar NaOH, right? This of, remember, means times. So if you are trying to figure out which goes on which side together, look for that of. If you look on the previous, right? Here's the of, which was connecting how many. So that was this times 12. And then here's the of in the blue, right? Connecting liters to that molarity. So here's our of. So 125 times 2.75 will equal what times what? So now we added 25 milliliters. So that means our second volume is 25 plus 125, which equals 150 milliliters. All right, so you can convert all these to liters, right? So 3 jumps, 1 through 3. So we have M1 is 2.75. Our V1 is 0.125. And our M2 is what we're looking for. We're trying to figure out what the molarity of this new thing is. And our V2 is 1.50 or 0.150 liters. Okay, so we're solving for this. So 2.75 times 0.125 is 0.343. So over here we got 0.343 is equal to M2 times 0.15, 0.150 liters. And so we're going to get M2 divide 0.343 by 0.15. And we get 2.29. So we're dividing both sides by 0.15. And we get M2 is equal to 2.29 molar. Okay, so the molarity went down from 2.75 to 2.29 because we put more water in it, which should make sense. All right, there it is. That is your thing. I hope it works well for you. Please let me know if you have any questions.